get started. First, want to talk about homework a little bit. So these data, as you know, were about presidential vetoes and overrides thereof in some cases. Certainly, this is something that is studied a lot in political science. But the people who study it are almost always, maybe literally always, going to be applying frequentist methods to data like these, even though these data are not a sample from any population. We actually have like every veto that's ever been recorded being reflected in the data set. Moreover, it's impossible to imagine there being any other data for this time period other than the data we have. Certainly there's going to be more presidents and more congresses and more vetoes and perhaps occasionally more overrides in the future. But that doesn't mean the past is a random sample. There's nothing like, no randomized process by which some observations made it into this data set and other observations that existed couldn't. If you just like divide the data, into data from the past and data from the future, the split at the present is not a randomization mechanism. It's just like the reality of it, that we can only collect the data once it occurs. This is in no way a random sample. What implications does that have? And one of the things I emphasize a lot, different classes, to avoid getting confused by frequentist stuff. Not so much because frequentist stuff is that confusing, but because it's so often the terminology is like misused and abused and whatnot. To just say, if you're talking about the proportion of possible data sets where some happens, have your sentence be the proportion of possible data sets, blah, blah, blah. And if you're talking about degrees of belief about something, say my beliefs about beta or whatever are normal under my prior distribution. And that way there's no ambiguity as to whether you're talking about the objective or the subjective interpretation of probability. Now, frequentists refuse to do that because they insist that their objective definition of probability or their definition of objective probability is the only legitimate one. So when they say, the probability of this or whatever, it implicitly always means the proportion of, possible data sets that could be randomly sampled from the population that have this property. It's just a shorthand for that, because that to them is the only legitimate definition of probability. So you can say a p-value is the proportion of possible data sets that would yield an estimate that is more extreme than the estimate that we obtained from our actual data set if the null hypothesis were true. You can say about confidence intervals, okay, for 90% of the possible data sets that could be randomly sampled from this population, 90% of them, if you applied the confidence interval estimator, would include the true value within their bounds, etc. So that is a good way to emphasize the frequentist interpretation of probability in order to not get confused by the statements that it makes. And if more people do that, then there'll probably be fewer people who would apply frequentist stuff in a situation like this, where it makes no sense at all to talk about the proportion of possible data sets when you have the only data set that is remotely feasible to have in your hands. There's no other data set on presidential vetoes and congressional overrides in the United States, other than the one you have, which has literally every observation since 1789. So any statement about like proportional of possible data sets is just going to be like 1 or 0. It's either true in this data set or it's not. So Fisher would say, probability is not applicable to this. And yet, people who ostensibly are followers of Fisher use Fisher's maximum likelihood and whatnot methods, despite that. And that seems very limiting in a manner of speaking, and it is. But you can sort of understand a little bit why, that wouldn't have popped up on Fisher's radar screen, because Fisher's substantive scientific research interests were mostly in agricultural experiments. And so there would never be a situation, particularly not in 1920, where you could say, like, I have every orange tree that could ever exist. And so you're trying to make scientific conclusions about like a species of orange tree. And you would not have like every instance of that species of orange tree, nor would you be concerned with making a scientific statement about a particular orange tree. But that's not exactly the way science works today. Saw an example, with the midterm, and you might say to yourself, well, when would anybody ever be concerned about like one airplane? Why wouldn't you say something about like the population of airplanes? Well, if you wanted to say something about the population of airplanes, like all of them would either be in the sky or parked at the airport. But we're concerned, which is an understatement, about a particular plane when it goes missing with 200 people on it, and as best we can tell, lands at the bottom of the Pacific Ocean. Now we're concerned about a particular airplane in the way we never would be about a particular orange tree or a collection thereof that's exhaustive. So you can see back before there was social science, Fisher really wouldn't have been concerned about the situation in which you have like all possible data that there might be, but particularly when social science started to become a thing in the 1940s or so, it would often utilize historical data, often based on institutions that people create, like the Senate or whatever. And you might have data, for all possible observations, or at least all possible observations since somebody started keeping track. And so you can get in this situation in which you have data you're interested in, you have some like scientific, social scientific questions about, but you don't have a sample. Even outside the social science context, with like modern, what you might call passive data collection, things that we have today with like servers and stuff like that, like every website that you go to, and even some websites that you don't go to, are going to collect traffic for literally everyone who clicks on it. And they have, what did you click on and when was it, and what the advertisements were showing at that time, and all that business since the beginning of that website. And so, it becomes more plausible to think of scenarios in which you literally would have all the data. But just because you have all the data doesn't mean you have all the answers. Because what you probably want to know, well, what are the values of the parameters in a model for this data generating process? what model would be best if there's like more than one model we could think of. All the 5 sources of uncertainty, only one of them pertains to the only sorts of questions that frequentism answers, which is, if I just have a small sample from a population, how can I make conclusions about the larger population from the small sample that I have? But that should, conversely make it even more clear that even if you do have a small random sample, which is incredibly rare in social science these days, there's a lot of data sets that are not random samples, and there are some data sets that are random samples but are not small. Because if you're going to go to the trouble of collecting a random sample, like in 2023, or even 2022, or even like any time in your lifetime, you're going to go big. Like, why would somebody like today take a sample of like 14 people? It happens in neuro, like sometimes because it's incredibly expensive to like MRI, fMRI somebody's brain as you do whatever you're doing. But for the most part, social science, if we're going to do a poll of public opinion or something like that, we're going to have a lot of people in the poll. Problem being with like non-random response rates, that's not really a sample either. But anyway, so there's all kinds of reasons why applying frequentist would not make sense in this context. For the same reason, like the midterm question on France and the PR systems and stuff like that, they had all the municipalities in France in 2008 or whatever it was. So this is not a sample of French municipalities. Moreover, the only reason why they didn't use all the municipalities that they had is because they did an entirely not random thing of just looking at plus or minus 3,200 on either side of the threshold for switching the local political system from a plurality rule to a PR thing. So chopping it off at 3,500 plus or minus 3,200 was a totally not random selection mechanism. So it was not a random sample, and frequentist methods shouldn't have been applied to it, even though they were in the original paper. And so why do people do that? Even people who should know better, even people who've personally expressed to me that their data are not a sample, in the case of Andy Eggers. But they do them anyway. And in part, in some cases, not so much Eggers, but other people, because they don't know anything else. In part because they didn't learn, or maybe they weren't even really adequately taught, that frequentist methods are, the way probability comes in is because it presumes that the data have been randomly sampled in some fashion. And in a lot of cases, that's not true, particularly in the social sciences. But also, big part of this is the willingness of scientists, particularly social scientists, to accept frequentist estimates and conclusions as if they were Bayesian, even though Fisher created those methods to prevent Bayesian methods from taking hold in the sciences, as the sciences in its modern formulation were being, congealed. And in some cases where the posterior distribution actually is kind of normal, then maximum likelihood estimates give you decent estimates of a posterior median. But that's an awful justification for using frequentist methods that way. It gets like the worst of both worlds. It's, the researchers are making subjective conclusions, like, the probability of the coefficient on PR being positive or something like that. That's not a frequentist question. So all of Fisher's criticisms, which were not very good criticisms, but they were understandable as to why somebody would have those criticisms, continue to apply if you're using Fisher's maximum likelihood for subjective conclusions. Like PR probably has a positive effect on turnout, or having more people in your party makes it less likely that you have to veto something like that. So it gets all of Fisher's criticisms, but doesn't get all the benefits of Bayesian estimation in terms of being able to put rigorous probability, albeit subjective probability statements, onto the conclusions we're making, when the conclusions we're making pertain to things that Fisher would say are not random variables, which in this case nothing would be. So that's I think a big part of the answer to some of the questions that we started the semester with was, why is Bayesian methods not used practically at all in the social sciences? Is because people are willing to accept frequentist stuff as a substitute for Bayesian, and if so, well, why would you go to the effort to actually learn, to actually do genuine Bayesian stuff if you can have this cheaper substitute? That it's not like it's as good, but everybody accepts it. So in terms of the model for the, what happens with the vetoes and the override, main thing to substantively think here is that it's not necessarily a linear in terms of how many seats which party has. A lot of it has to do with which party has the majority of the seats in the House and or the Senate. So whether or not you're below or above 50% is a pretty huge consideration, because whichever party has more than 50% or 50% or more in the case of the Senate is going to be able to control what bills come up to a vote. And so if the president's party controls either the House or the Senate, it's pretty unlikely that there's going to be many bills that the president disagrees with, because if the president does disagree with them, they're probably not going to get a vote in the first place, and so there wouldn't be an override. But if the president's party controls neither the House nor the Senate, then there could be a lot of opportunity for bills that the Congress would pass that the president would oppose and veto, and maybe get overridden, but probably not that much. And so should really think about the interaction in terms of who controls the House and who controls the Senate, as far as affecting the conditional expectation for the number of bills override in a Poisson/negative binomial process. But then when you get into, okay, is a veto going to get overridden? Well, one, if you're considering whether to override, it means already half have supported the bill the first time around, sort of irrespective of who controls what, and also you need 2/3 to override. So the 50-50 thing is less salient on the override part, and maybe it sort of depends on just how many people in Congress are supporters of the president. And as many of you encountered, it can be difficult in count models to keep the conditional expectation from not going to the moon. And you can shift the intercept over to the left, that's the left for you. And that helps a little bit. Part of the deal here is the asymmetry of the exponential inversing function. So in linear models, we sort of said, well, you can think about the intercept relative to centered predictors as the expectation of the outcome for an observation with average predictors. But that in a linear model is not too different from, okay, what's the expectation of the outcome irrespective of the predictors? it's a different concept, but it's not really much a different number. And so if you just think, okay, what's the expected outcome irrespective of the predictors, that's a good weakly informative prior for the actual intercept, which is relative to the average predictor. But in a generalized linear model, particularly one with an asymmetric link function, such as log in this case, it can be more imperative to think about it correctly. So what is the logarithm of expected regular vetoes given an average Congress? And so an average Congress, it's probably going to be pretty evenly split. Maybe the president's party controls like one, if not both, of the houses of Congress. So there's probably not going to be that many vetoes for an average Congress. And almost all of the vetoes, and consequently the average number of vetoes, is going to be coming from non-average Congresses when the president's party controls neither the House or the Senate. So you do have to think a little bit more rigorously about the intercept in that situation. But as long as most of your prior predictive distribution is in the reasonable regime, it doesn't matter too much if the maximum, most extreme draw that you get from the prior predictive distribution is, something a little crazy. So, we can take the averages of the variables, including the average of the interaction between House minority and Senate minority for the president's party. And we can draw from the prior distribution. Again, we don't want any of these to really be too far away from zero in order to keep the eta in close to zero, if not negative territory, so that the anti-log of eta is, reasonably small number. So we can do that for the parameters in the vetoes part of the model, and then also for the parameters in the overrides part of the model. In the case of a binomial, the logistic link function or inverse link function is symmetric. So again, it's a little bit easier to get away with thinking, okay, what's the probability that a veto gets overridden irrespective of Congress, as opposed to conditional on the average Congress. So anyway, I put in 5% of that, applied the inverse CDF of the logistic distribution to get the log odds for an average Congress. And then, I have some coefficients depending on the president's party, how many seats they have. And then once you have the realizations of the parameters, you can go row-wise and get, realizations of eta for the regular overrides part, anti-log the eta to get the expected count of overrides, multiply by realizations of the errors from a gamma distribution with shape and rate equal to phi, and then draw from a Poisson whose parameter is the product of the expectation and the error to get realizations of the number of regular overrides. And then you can use that realization of the number of regular overrides as the size parameter in a binomial distribution to draw the number of overrides from between 0 and the number of regular vetoes. It's going to be an integer somewhere in there, and the probability of overriding any one of those vetoes is this log odds function here, stuck into the inverse CDF of the logistic distribution to get probabilities between 0 and 1, but a lot closer to 0. Yeah?
For drawing the number of vetoes, I was wondering about an offset term because 118th Congress has only served 12% of its total time.
Yeah. That could have made sense. It would only be for 1 out of 118, but yeah, technically that would have made some sense. Anyway, this is the essence of it. And the essence of it is not that different from bowling. Really nothing is. In the sense that, okay, now we have a more complicated process that goes into the expectation for how many vetoes there are in like the first roll. And then what happens on the second roll depends on how many opportunities there are, regular vetoes, to then override. So is this still like first step, second step business? But really, all of Bayesian inference is like that, in the sense that like first step there's priors on the parameters, and then second step there's draws of observables conditional on realizations from those priors. And that's how we set up generative models, and once we have the generative models, then we can go about conditioning on data from the wild to update our beliefs about the parameters in those models. And so if you plot this, you're probably going to have like occasionally overrides being like more than 1 million, but almost all of it should be in a pretty like small range. So you can just truncate, at some point. And then if we look at these plots here, it shows which makes sense if the president party is not in the minority of either the House or the Senate. Basically, there's going to be 0 overrides because there's going to be basically 0 vetoes in the first place. If president's party is in the minority of both the House and the Senate, then a lot more can happen, and it does kind of have a long tail. That kind of makes sense. If the president is in the minority of one but not both, the House and the Senate, then it more resembles the case where they control both, because effectively one of the parts of Congress is going to mostly prevent the bills from ever being considered in them, but maybe there's like a little more probability. So overall, I would say that's totally reasonable enough to then condition on the data that you have. Need to make sure that your priors on the parameters are in the same order that R makes columns of the X matrix, and in particular R is going to put interaction terms at the end, even if you try to put them at the beginning. So just watch out for that. I didn't think there would be a huge amount of over dispersion in this case, but it actually sort of turned out to be. So this might have been a little bit confusing, but it's only confusing because we force ourselves to be compatible with the function that we're emulating, which in this case is in the mass package. And what comes out of the mass package is this thing called reciprocal dispersion, which is the reciprocal of phi. And so we can just get the draws of reciprocal dispersion, take the reciprocal of them. Now we have draws of phi, which average like 2.75, which is certainly not infinity, which is what we would need for negative binomial to coincide with the Poisson, or in other words, for the errors to all be 1. No variance. So yeah, the errors are going to have a decent amount of variance here, which helps explain why like sometimes we get a lot of vetoes, but most of the time not so much. And then if you wanted to counterfactual, well, what if the Democrats only had 49 seats in the Senate right now? Just make a tibble that corresponds to that counterfactual scenario, make the predictions, plot them. In this case, it's giving about a 25% chance of no vetoes. But after that, kind of anything can happen with a long tail. And you might say, I don't know how much I agree with that. And that would be a good intuition to have, but you need to keep in mind that data generating processes can change. we assumed sort of a homogeneous data generating process starting from 1789 and going up through and past 2022, but there have been episodes in American history where things sort of fundamentally changed, one of which was the Civil War, where like we can't even really figure out how many people were aligned with Andrew Johnson after he took over when Lincoln was assassinated, because like everything was in flux. But also today, you know, with Congress, they use the filibuster differently than they did in the long historical past. So it sort of used to be the case that one party would filibuster in the Senate only if they had like a really, really strong objection to a bill being considered, such as granting civil rights. But nowadays, or maybe not nowadays, but in the past 20 years or so, filibusters have been very routine for bills that can be filibustered. Not all of them can. And so that's really changed the way the dynamic of the Senate would be. And it is entirely plausible that if the Republicans controlled both the Senate and the House, albeit only by slim margins, they would be proposing a lot of bills that Democrats would disagree with, and Democrats might be, in the Senate, might be inclined to filibuster. But it wouldn't be surprising at all if Republicans excluded those bills from filibuster consideration, in much the same way Democrats have done, you know, when they have been in power. So yeah, like the data generating process can change, and your model should reflect that, even if, you know, the homework didn't require that of you. And so overrides, binomial model, logit link function, and you can get out posterior probability of overriding any bill vetoed by Biden and the current Congress by applying the inverse link function to the linear predictor. And you should get something with a very small probability, although you might think it's even smaller than this. It's hard to imagine there being 2/3 support for anything Biden opposes in a Congress that's pretty much 50-50. Questions about any of that? Okay. So let's start talking about model checking and comparison, which was on the syllabus for this week. Before we do that, we should remind ourselves again that I am subject to Columbia's conflict of interest disclosure regulations. And today might be as good a day as any to also mention the fact that, you know, criticisms of things that are not stand could also implicitly be seen as attempts to get more people to use stand. Because today is one of the days where we're going to have to get even more real than we otherwise would about some of these other quantitative methods that are used in the social science and elsewhere. But before getting too far into that, I'm sure many of you noticed today that the U.S. government announced estimated GDP for the fourth quarter of 2022 was 2.6%, down from 2.7%, which was the estimate a month ago when we did homework 2, I guess it was. And the question I wanted to ask on homework 2 was about the difference between GDP estimate and the GDI estimate, except I forgot that they don't announce the GDI estimate in March for the fourth quarter, but today they came out with the first GDI estimate for the fourth quarter of 2022, negative 1.1%. And as we said on homework too, both of these are equally plausible in theory. Maybe the errors for GDI are slightly small in general. Maybe GDI does a better job of accurately estimating things when the economy is transitioning from a higher growth regime to a lower growth or maybe a recession regime. But conversely, maybe GDI in the fourth quarter is a little bit worse than it is in the other three quarters because of like year-end tax accounting when some things accidentally get counted as wages when they should be capital gains or vice versa and some stuff like that. So yeah, there's like criticisms that could be made either way, but bottom line, we have rather large difference between the government's estimate of GDP and GDI, and moreover, those rather large differences are on opposite sides of zero, which is certainly a salient, if not substantively important threshold. This, despite the fact that, as we saw in homework 2, Oken's law would suggest economic growth in the fourth quarter was closer to 3.5%, owing to the fact that the unemployment rate declined a little bit during the fourth quarter from like very low to still very low. And if workers are hiring or employees are hiring more workers, it stands to reason that those workers are producing more stuff and more people are buying the stuff that those firms are producing. So a lot of stuff stands to reason, but things that stand to reason can be in contradiction with each other, and the Bayesian framework gives you a way to, I don't know, I would say reconcile, but at least condition on data, even if those data are contradictory to each other, to give you an updated set of beliefs about what the true percentage increase in growth was in the fourth quarter of last year. And if you form your prior based on Oken's law, then your posterior beliefs about the true economic growth rate ought to be much closer to GDP than they would be to GDI. GDI more inconsistent with Oken's law in this case than GDP is. But if you don't have a framework for reconciling those things, or like managing the fact that the different sources of data are telling you different things, and again, the data is not like raw here, it's coming from the government's model, then what do you do if you're just like, there's three different numbers? One probability distribution. So we'll come back to that. But anyway, the material for this week about model checking, model comparison, things like that. You probably have noticed, but people often try to distinguish like what quantitative methods you should use when, based on the nature of the data. So there's a lot of people that feel, well, if you have like a randomized controlled trial, you should use Fisher's design-based inference, also called randomization inference. And if you have a survey that's representative of a population, then you should use frequentist methods. And if you want to predict the outcomes as opposed to saying something about the parameters, then you should use supervised learning, because that's really what it's geared for. And like if you were going to use Bayesian stuff, if at all, well, maybe you should use it in situations where you don't have a lot of data, but you do have strong priors. Like maybe if you're playing poker for millions of dollars, or you're looking for a 737 that went missing, or something like that. Then yeah, maybe use Bayesian. But Bayesian inference, as we said many times before, is a system for belief management. It's not as if we like customized it to be applicable if you only have like one data point to condition on. We made it coherent for each data point that you condition on. And so it should be applicable to situations in which you have like more than a little bit about a data. And because we're conditioning on the data, yeah, you should take into account with your generative model how the data came to be. Like thinking about the president and the House and the Senate and all that, or the path of the airplane. Or, you know, if it was a randomized control trial like it was with the Pfizer and BioNTech thing. Yeah, you should take all that into consideration, but because we're conditioning on the observed data, the Bayesian approach ought to be applicable to all these things, and that, you know, from a Bayesian perspective means, well, if we learn this general one, then it would be less important to learn all these different sorts of methods that have been customized to particular data situations, and it would, you know, make it easier for students if they didn't have to learn a zoo of different techniques. If they could just learn like one and apply it to a zoo of scenarios. So looks like one word got cut off, but the gist of what I was trying to say here is Bayesians can and should and do generate predictions. And so this week we want to particularly contrast that with supervised learning, which, you know, also generates predictions, but in a manner of speaking, that's kind of the only thing that supervised learning is trying to do well. And so from a Bayesian perspective, supervised learning is like frequentism but without probability. Now that's not how supervised learning people would describe themselves, but from a Bayesian perspective, that's what it looks like. And so if you take the probability out of frequentism, then there's no p-values, there's no confidence intervals, there's no standard errors, none of that. All that's left is the point estimates that are obtained by optimizing some function, and then to use those point estimates to generate predictions for future data, or what stands for future data. But if that's your main goal as opposed to anything pertaining to the interpretation of the parameters or being probabilistically uncertain about the parameter values or anything like that, it frees you to do a couple of things. One is to add a penalty term in the objective function. So most of this supervised learning stuff, it starts with like a traditional log likelihood function, even though there's no real reason why it would need to if you're getting rid of probability, like why you would start with a log likelihood function, but most of the time that you do in practice. And then you can add a penalty term to that log likelihood to get these penalized maximum likelihood point estimates. But the other thing it frees you up to do is to explore forms that are considerably more flexible than linearity. And you know, you can do that with frequentist stuff as well, but then it becomes very hard to derive the distribution of a test statistic if the function is some like thing that doesn't have a whole lot of assumptions about it, just like it's continuous or something like that. And so you'll see, particularly these days, a lot of neural networks and random forest and support vector machines and whatnot that have a very nonlinear relationship between the predictors in the original data set and the outcome, whether that's continuous or whether that's, you know, binary or whatever. But due to this additional flexibility, it becomes basically a rule that you need to split the original data into training. Should usually constitute about 80% of the total observations, and testing data, which would be whatever is left. And the training data are used only to obtain point estimates of the parameters. The testing data are not used at all to obtain the point estimates of the parameters. And then the testing data is used to evaluate how well those point estimates generate predictions in the held out data. But there's another aspect to it, which is the penalty terms are usually, or penalty functions are usually gonna have some tuning parameters in them. And so you're usually gonna wanna subsplit the training data even more into k-folds, or sometimes people use bootstrapping to choose the tuning parameters that go into the penalty function in some fashion. And so all this is geared toward being able to make predictions in the testing data and then evaluate them. And a lot of people who are not Bayesian make claims that this supervised learning process is or resembles Bayesian inference. And from a Bayesian perspective, that, like an actual Bayesian perspective, that seems ridiculous. Like, is there a posterior distribution? And then it's not Bayesian. Like, what were the priors? Well, we didn't really specify those explicitly. How did you figure out the denominator of Bayes' rule with the impossible integral? Well, yeah. So, it's not a Bayesian process, and particularly because it maximizes a function in the training data to produce a point estimate of the parameters, which is then used to make predictions in the testing data. And that fact alone is what I think makes it fundamentally like frequentist estimation, but they just dropped the frequentist inference in terms of hypothesis testing and stuff like that. It brings in probability to it. But the fact that the whole training data business yields a point estimate rather than a probability distribution or a whole bunch of draws from that probability distribution is what makes Bayesian and supervised learning things, I would still say, fundamentally different, even though you'll sometimes see like Bayes' rule pop up. Some of this artificial intelligence stuff has like Bayes' rule going on in it, but not with like a probability distribution over theta. And another thing that yields some people to make analogies between supervised learning and Bayesian stuff is that the penalty functions that are used in supervised learning are often, not always, but often some prior density, the logarithm thereof, or a kernel of a prior, that may condition on an unknown tuning parameter. And I linked to a paper here by Sarah, whose name I forgot, Van Erp, no too many Sarahs, has this table in it, pointing out the correspondence between various penalty functions that are used in supervised learning and the prior PDF that they would correspond to, which is always conditional on some tuning parameter that I referred to before, lambda. And so people say, well, adding a penalty term is, it yields the same, or it could yield the same numerator as in Bayes' rule. So that makes it, Bayesian. But these penalty functions actually, for the most part, make for poor priors. And the reason why that is true is because the penalty functions in a supervised learning context only matter at the optimum, because the optimum is the only thing yielded by the training data process. So it shifts, the penalty function shifts the suprema from like one place to another place. But in supervised learning, there's no concern for, well, how does the penalty function affect the objective away from the suprema, like out of the tails and stuff. Whereas from a Bayesian perspective, what happens out of the tails is very important. It affects like posterior means and posterior medians and stuff like that pretty strongly. And so these penalty functions, when you sort of reinterpret them as particular priors, often correspond to some rather weird beliefs overall, even if they kind of make sense at their mode. And to see this, let's do an example with sort of a Bayesian flavored version of lasso. So it involves this function here, which is the PDF of the so-called Laplace distribution. And Laplace was more Bayesian than Bayes was, so surely this will be something that resembles Bayesian analysis. And if you set it up as a generative model, then it looks similar to what we've done before. Let's say continuous outcomes. So we have eta plus epsilon being the observed outcome. Epsilons are drawn from the normal distribution with unknown standard deviation sigma. We have the same business that we've had before in terms of constructing the linear predictor. Since it's Gaussian, we don't need an inverse link function here. We have some prior on the intercept relative to center parameters, but what's different is our construction for beta, which is now this weird business, where theta is drawn from a uniform distribution between -1 and 1. We have a similar, let's say, exponential with rate r prior on sigma, which governs the standard deviation of the errors. But in this formula, sigma also appears in the denominator here for the construction of beta, conditional on lambda and sigma and theta. And you might say, well, why do we do that? I don't even know what that formula really means. Well, it's a way to draw from the distribution whose PDF is this here, corresponding to the lasso entry of the table, which is the so-called Laplace distribution, and we'll see what it looks like in a minute. But in terms of the code to draw the parameters, okay, you can do what we've done before. Just start from the bottom, go to the top, apply the formulas. So draw theta from uniform, draw sigma. But what I omitted here is, well, what's the prior on lambda, which goes into the construction of beta, but otherwise doesn't affect anything except each of the beta k's. And one choice for that might be exponential distribution with some relatively small expectation or something like that. And once you have realizations of lambda, then you can use them along with the sigma and the theta to construct beta. But one among several things that is going to make this Bayesian generative model different from what supervised learning does is that Bayesians are going to have to commit to a proper prior distribution on lambda, whereas the supervised learning people, like they do with everything else, are going to take lambda to be a point rather than a whole bunch of realizations from a probability distribution. But we could follow this generative process, and if we do, we could get a plot of the draws of beta. So this came out weird. This is supposed to cross out both the lambda and the sigma. So this is the marginal distribution of beta under the prior, under our model, but irrespective of lambda and sigma, because I took a bunch of draws. And you look at this and you might say, that might be something I could actually believe about beta. It seems like a normal distribution that's kind of been like squished in the middle so that there's like more right around 0, but it's got its like tails pulled out a little bit. So there's a small probability of it could be like pretty far from 0. And you might say, well, I could imagine situations in which that would look like a reasonable prior for beta. And yeah, it kind of might be. But that's thinking of it from a Bayesian perspective. From a supervised learning perspective, you don't get distributions of any of these things, you just get point numbers. And so, as usual, no ability to convey any uncertainty about them or things like that. So how does supervised learning people choose the tuning parameters and their penalty functions, lambda? Like I said, first you split into training and testing with, much more in training. It doesn't have to be exactly these ratios or whatever. And then you further split the training data into k-folds that each have, the same number of rows in them. You make some sort of guess for lambda. Then you solve for the parameters in each of the k-1 folds. You predict the outcomes in the kth fold. You average the loss over observations. There's k ways to hold out one fold, so you can average that there. And then that might suggest an algorithm where you could improve your guess for lambda and then repeat the process over until your guesses for lambda and beta become pretty stable, in which case you could stop. And so now you have a guess for lambda, a guess for all the betas, etc. And you can then use those guesses of the betas to predict the outcomes in the testing data, average whatever loss function you want to do over the M2 observations and testing. So once you have the parameter estimates from applying various algorithms to the training data, and so the training data is only used for obtaining the parameters, and after you have that, then you only use the testing observations to evaluate how successful this model is at predicting stuff with respect to some loss function. And that loss function can and reasonably often is the log likelihood, or the log likelihood multiplied by -1, but same idea. And so one of the most popular loss functions is mean squared error in the testing data. That's all. Testing data. So the sum of the squared errors in the testing data, where eta is going to be a function of the betas that you obtain from the actual training data. But as we can see, the mean squared error concept is proportional to a Gaussian log likelihood, just like multiplied by -1, and you have to have some estimates for sigma and stuff like that. But it is telling you the same thing. More common than mean squared error, you see root mean squared error, which in a manner of speaking is an estimate of sigma rather than sigma squared, but square root is just a monotonic transformation. That's not going to change the ranking of models with respect to how well they predict the outcomes in the testing data. So that's probably the most popular loss functions for continuous outcomes. With binary outcomes, the loss function is usually going to be some function of the proportion of correct and incorrect classifications, where an observation in the testing data is classified as success if eta is positive, and classified as failure if eta is negative. So you get these binary classifications that you can then compare with your binary outcomes. It's often arranged in a so-called 2x2 confusion matrix, where you have along the diagonal the number of correct, or the proportion of correct classifications, both the successes and the failures, and then in the off diagonals you have the rate of false positive and false negative, and a whole bunch of different functions can be applied to those four numbers. It all have different names and stuff like that, to get area under the curve and all sorts of stuff. So we don't want to get too bogged down on the differences between the loss functions. We just want to note that they exist, and they're used to compare different models based on how well they predict in the testing data from the point estimates of the parameters that were all obtained from the same training data. So you only split training and testing off from each other once, can apply a whole bunch of different algorithms to obtain different sorts of point estimates, and then see how well they do predicting in the testing data. But from a Bayesian perspective, there's really only one function. Maybe if you had like a very specific reason, you could use some other one, but certainly a generic default choice for utility of prediction would be the logarithm of the density or mass, depending on whether the outcome is continuous or discrete, of the future data. Same distribution that we used in the generative model, but now we're thinking about, applying it to the future. And so, so first of all, you're going to encounter people who say, well, yeah, that's a reasonable utility function for future data, but we don't have the future data in the present, so we need to use lasso. Which is like the same absurd statement as to say, well, how can someone play poker if you don't know what the other person's cards are? Or how can we know what the temperature is going to be 100 years in the future until 100 years from now? And those are absurd because we can take the expectation of a function in the present over the future in order to make a decision in the present about what to do. And so decision theory, as we talked about earlier in the semester, says, well, you've got your utility function, make the choice, in this case, a choice which model to go with, that maximizes expected utility. And so that gives us the expected log predictive density, the ELPD. It's the expectation with respect to future data of the logarithm for all the future data conditional on all the past data. And if the observations are conditionally independent, we can just write that as a sum of the integral over the outcomes, the log density or log mass of the future observation conditional on all the past observations, weighted by the conditional distribution of the future given the past. And we can do the Bayesian hokey pokey, where you stick the thetas in and you integrate them out to obtain the conditional distribution of the future given the past. And so, yeah, like the integrals are usually impossible, but we can approximate those very well by considering the logarithm of the density slash mass for the nth observation conditional on all the past observations but the nth. So here I'm using the negative index the same way you do it in R to indicate all but the nth observation. And so that approximation would then be the sum of the logarithm of the posterior predicted density, conditional on the parameters, weighted by the posterior density of the parameters conditional on all the past data, but the nth observation, integrating out theta. And this approximation here is going to be quite good if n is not small, because the expected log predicted density for any future data point, conditional on all capital N past data points that you have, is not very different from the conditional density slash mass with the logarithm thereof of one data point that actually was from the past, conditional on all the other data points from the past. So this approximation is only like one conditioning observation different. But the last line is somewhat feasible because this business here is just the likelihood contribution for the nth observation, which we know how to evaluate. So if we could somehow get the posterior density of the parameters, conditional on all the observations, but the nth, we'd be ready to go. And we actually can estimate that by reweighting the draws that we get from the posterior distribution conditional on all the data. That entails, it's got to be a supervised learning person following. That entails making an additional assumption. It's an assumption we can check, but it is an additional assumption that was not necessary in order to get the posterior draws. And that is, it's an assumption necessary to estimate the ELPD, which is assuming the nth observation on the outcome does not have too big an influence on the posterior distribution. So it just has like a moderate to small influence on the posterior distribution in isolation. If so, we don't actually have to estimate in different capital N different posterior distributions here in order to evaluate this, because that would take a long time and something would probably go wrong and it'd be numerically unstable and all kinds of things. Instead, under this assumption that's added, we can just get the posterior distribution once, conditional on all the data, but the assumption gives us a way to reweight our draws for what if we did not condition on the little nth observation, and now we get like a different set of weighted draws that we could use to evaluate our estimator of the expected log predicted density in order to compare different models based on how well they are expected to predict future data over all possible things that the future data could be. And that was talked about in the reading. Don't want to go into too much detail about the math of that, but it involves the Pareto smooth imported sampling business that was talked about in the reading. And also this estimator of the ELPD can be seen as k-fold cross-validation, where k is equal to n. And so leave one out cross-validation is a term you'll hear from supervised learning, but ironically supervised learning people don't utilize it very much. They usually do k is 5 or 10 or something like that, as opposed to capital N. So anyway, let's consider a posterior distribution for a model that comes from the National Election Study. This is a survey that's conducted shortly after every presidential election and asks people a whole bunch of questions about whether they voted, who they voted for, why they voted for that person, etc. It has income as categorical, so we want to treat that as a factor rather than like numbers, 1, 2, 3, 4, 5. Also has the age of the person, and as usual, I prefer to make age in units of decades rather than years, because essentially a 1-year difference between people is too small to really think about how that would affect how they vote. And so these are binary data. We can aggregate them up a little bit, use a binomial likelihood by counting up the number of people who vote for the Republican candidate for president in year 2000, which was when George W. Bush was running for the first time, and the number of people who vote or prefer to vote for Al Gore. And then we can use like a logit model for that, with this construction for the number of people who favored Bush, number of people who favored Gore as a function of the voters' age, their squared age, income category they're in, and binary variable as to whether they're white or not white. We can have some priors. And then once we get the posterior draws of that, we can pass that to the blue function, which performs this estimate of leave one out cross-validation that I was referring to on the previous slide and is talked about in more detail in the reading. And we get this Lu-based estimate of the expected log predicted density of negative 362.4. And as particularly the McElrath reading pointed out, this number in isolation doesn't mean anything. It's only the difference between this number and the corresponding number produced by a model for the same outcome that is meaningful in terms of expected KL divergence from the target business that was talked about in the McElrath reading. So you don't want to try to make any sort of absolute interpretation here. P-lu is an estimate of the expected effective number of parameters, and it's derived from the same process that gives us so it's not additional, it's just like supplementary information. And this business about effective parameters will become more important as we get to the last couple weeks of the semester, but it basically says, well, this is about the same number as we would get from a model that had like 7-ish parameters, but no prior information. And so when you have prior information, in this case it was too weak to make much of a difference, but when you have stronger prior information, the effective number of parameters can be a lot smaller than the nominal number of parameters. And basically saying, okay, we get about the same amount of predictive accuracy as a model that has like 7 parameters but no priors. Even though the nominal number of parameters may be, I guess is in this case, a bit bigger than 7. But anyway, that's just supplemental information. And really redundant information is this LUIC business, which is literally -2 times this, but that puts it in the same units as the AIC and the WAIC and the DIC and a whole bunch of other things that have acronyms that end in IC, where the preferable model on those criteria is the one that has the smaller AIC. But this is just that multiplied by -2. So from the way we look at it, the preferable model is the one that has the higher ELPD, even though the ELPD sometimes, actually often is negative. So whatever is closer to 0 would be preferable. And so one way among many in which this could be used is you might say to yourself, well, how do I know whether to use a logit model or a probit model for Bernoulli or binomial data? You could answer that question by doing a comparison between those two models using the proto-smooth imported sampling leave one out cross-validation estimator of the ELPD, even though that's a lot to say. It's not a lot to do. All you need to do is change the link function to probit. Maybe scale up your priors by 1.6 because that's usually how it goes when you switch from logistic errors to standard normal errors. Get those posterior jaws, call the LU business on that, and then pass both the LU for the logit model and for the probit model to the LU compare function, which in this case will tell you unambiguously that there's very little difference in the expected utility if utility is based on the log density of future data between a probit and a logit model, and in many, if not all cases, that is so. But if you had to choose just one, in this case the probit model is slightly preferable because the difference in the ELPD between them is a little bit negative or lower for the logit model than it is for the probit model, even though the standard error and the difference is like more than twice the point estimate there. But anyway, so if you had to choose just one, in this case, maybe the probit model is a little bit better in terms of expected prediction of future data, but you don't have to choose just one. Because as the reading from Yuling, who used to be a PhD student here at Columbia, a couple others pointed out with the stacking business, well, you could take a weighted average of the predictions of these two or even more than two models for the same outcome. And the weighted average of those predictions may have a higher ELPD than any of the models in isolation. So to choose just one, in this case the probit, would be to put like 100% of the weight on probit and 0% weight on logit. Whereas it would actually be a little bit better in terms of ELPD to put 30% weight on the predictions from the logit model and 70% weight on the predictions from the probit model in this case. Because we can easily choose weights to maximize the ELPD once we have draws from all the candidate distributions. And particularly when you have models that differ by more than what a logit model differs from a probit, you can get better predictions using the stacking weights business, because like some models may be different or better or worse, whatever, for different parts of the data. And so by taking this weighted average, you can sort of upweight the better parts of each of the models to come up with predictions that are better as a whole. It's also useful if you have like annoying co-authors who have like ridiculously strong beliefs about how the model should be. It's often easier to just do this and it comes out with like a 2% weight on their preferred model and like 98% weight on something that like the rest of the co-authors think is reasonable. It's easier to do this and just say, okay, 2% weight is not going to hurt anything, than it is to actually convince an extraordinarily stubborn co-author that they were wrong. You can just take a weighted average where they get very little posterior weight, if in fact they were wrong. Probably. Questions about this so far? Or a little bit of the derivation that led up to it? So if we do that, we're in the same position as the supervised learning people are in terms of being able to compare models, provided they are estimated on exactly the same outcomes. This is not appropriate for comparisons between models on different outcomes, even slightly different outcomes. It has to be literally the same outcomes in order for the stuff in the McElrath's reading about interpreting differences in ELPD as KL divergence stuff. But anyway, so another thing that is useful with the Pareto smooth leave one out cross-validation estimator of the expected log predictive density is that they can be used for posterior predictive checking, although I have to sign into my computer again and regenerate the plot. So they can be useful for posterior predictive checking. And that's because these Pareto smooth importance sampling weights, if you pass them into their own CDF, should be distributed uniform when the model is so-called calibrated well, which is to say, like, if your model says there's a 30% chance of something happening, then in the data, like when those conditions occur, there should be about 30% of the observed observations exhibiting that. And if your model says like there's an 80% chance of this happening in other situations, then when you look at the data under those conditions, you should see about 0.8 of the observations exhibiting that. And when that is true for like the whole predictive space, then we say the model is well calibrated, and Bayesian models are well calibrated if you're estimating the correct model. That's like a mathematical fact. And so we can attempt to verify that by looking at the distribution of these Pareto weights that have been passed into their own CDF, as compared to standard uniform weights that we just draw from the standard uniform distribution, and it looks like this. So in this case, even though the probit model is expected to predict slightly better than the logic model for future data, it itself is not fitting the data that good. Too few of its Pareto smooth important sampling weights are small. Too many are big to be consistent with this theoretically correct standard uniform. And so that can help us as a additional diagnostic as to whether our models are well calibrated. And in general, anytime you have the opportunity to use something with a lu prefix, it's going to be better than the version without the lu prefix, because the lu means, okay, what if we left out the nth observation and proceeded, estimate, and then poke that through. And so it doesn't always make a big difference in like reality, but it makes a big difference in people's minds who are allergic to the idea that you might use the same data twice, like to use the same data to estimate the model as you would to evaluate the model. Because in a supervised learning context, that's a big no-no. And so if you can say, no, this is like predictions for what if we left out the nth observation and used the rest of them, then it sidesteps that reflective criticism. And it's the same deal that you see that McElroy's reading, harshly criticizing the use of R squared, even though it's mostly frequentist use of R squared, because you can just make that bigger and bigger and bigger by including more parameters in the model. It doesn't mean you're predicting future data any better. And so the problems that McElroy points out can be averted by calculating a posterior distribution of the R squared using the leave one out cross-validation concept, asking ourselves, well, how well do we predict the nth observation from the posterior distribution conditional on all but the nth observation? And that is somewhat similar to a Bayesian version of R squared. You can calculate both of them, but the lu one is preferable on those grounds. And here we see, it has a posterior distribution where perhaps we're explaining half of the variation in voting intention, but as we see from here, only half. And the half we're missing seems to be not like random. So we get this not uniform looking distribution of the cumulative probabilities of our Pareto smooth imported sampling weights that we used for that. So anyway, okay, so now we got the tools from a Bayesian perspective to evaluate our models, and in a manner of speaking, a similar way to how supervised learning people evaluate their models. Main difference with actual supervised learning, we would need to chop the original data up into training and testing. Use the training data to obtain the point estimates, using the testing data to evaluate how well the model predicts. And the testing data, you have to keep in mind, it came from the past, but it's supposed to be a proxy for future data. And so you don't use the testing data to get the parameter estimates, you only use the training data for that. But then you're using the testing data as sort of a proxy for future data to see how well those point estimates generate predictions, in hopes that the model that's best on that criteria is the model that's going to predict the actual future data better than those other models. But always remember, testing data is actually from the past. So if the data generating process changes between now and the future, then your models very well may not predict as well as they seem to predict in the testing data from the past, when the data generating process was the same as it was with the training data. Yes?
So how can you make sure to find like a relevancy of data that you know isn't going to change too much in the future in
Right.
Like, how can you verify that your data is gonna be like suitable for your experiments?
Right, so there's nothing we can do about the future. Stuff may very well change. Like, we haven't even talked about that we had a banking crisis since the last time, you know, in which like the data generating process for funding of startups like fundamentally changed because the bank where all the went. So the future can always be different from the past. And you as a researcher have very limited ability to control that. But what you as a researcher do have the ability to do is one, split your data into training and testing. But that's actually bad from a Bayesian perspective because we want to use all the data to get the most precise posterior distribution of the parameters given the data, all the past data that we can, because we have an estimator as to how well this is going to work for future data, again, assuming that the future data generating process is reasonably similar to the past data generating process, but we don't need to hold out 20% of testing data in order to make that conclusion, because we can just take expectations over future data instead of holding out data that's going to be a proxy for future data. And Bayesians can do that because they have a probability foundation underlying the whole thing that allows you to take expectations. If you try to do like frequentism without probability, there's no expectations. There's no probability weighted average of stuff over the parameters if you don't have a distribution of parameters, which you most certainly do not in the case of frequentist estimates or supervised learning estimates that yield point estimates from the training data. So as to compare this with Lasso, it'd be very similar to ElasticNet, which has gotten more popular than Lasso recently, or really any supervised learning thing that has a non-differentiable penalty function. This is implemented probably multiple packages, but this one is kind of the original implementation in the GLMNet package, which because it's like Stanford, it takes a matrix rather than a formula, so we're just going to use the same X matrix and Y vector as we did in the Login model, taking out the intercept because this thing by default is going to put the intercept back in. We specify family binomial because again, this was counts of the number of people who favored Bush and Gore, whatever. And we get these coefficients from a Lasso model for different levels of lambda. So this is like 10 different levels of lambda in the columns here. And so values of lambda that are greater than 0.5, which is all the ones over here, all the estimated coefficients are 0 at the optimum, except for the intercept, which is kind of not that important, and the coefficient on is the survey respondent white, or not white. But for smaller values of lambda, there's less penalization, and so some of the other coefficients on like income or whatever become not zero. But that sort of pushes back the question, well, what value of lambda is going to be optimal here? What point value of lambda is going to be optimal here? And for that, you need to do some k-fold business or whatever within the training data to ascertain what value of lambda is going to imply coefficients beta that yield the best classification in the held out fold, and then you can do it again for the testing data as well. But thing that I want to come back to, what makes this different from any sort of a Bayesian thing, like what we were talking about at the beginning with this generative model here. Here we had a prior and consequently, once we condition on the data, a posterior distribution of lambda. We get a whole bunch of draws of lambda that are weighted appropriately in light of the data. So rather than picking a single value of lambda, we just go with all the values of lambda and whatever they imply. It's not how supervised learning does it. They don't have probability. They don't really have posterior distributions. They just have point numbers. And so the question that they ask themselves, how do I arrive at a point number for lambda? And like I said, and like many other people have said, supervised learning is primarily concerned with prediction of future data, rather than any sort of interpretation. But things like lasso, other things with this non-differentiable penalty functions have an alternate use, or they've come to have alternate use, as a contrast to the frequentist procedure for deciding whether or not a predictor should or should not be included in a model. And the quote-unquote frequentist procedure in practice is to proceed as if a coefficient is 0, unless you reject the null hypothesis that it's 0. But if you do reject the null hypothesis that it's 0, in that case proceed as if the true parameter is exactly the estimate of the parameter by least squares or maximum likelihood, whatever it might be. Now, as we said before, but it bears repeating, the frequentist procedure, it's not frequentist. This is a realization of a random variable rather than a constant. Like if this was specified, pre-specified in advance, what to do, if it's not 0, then it could resemble Neyman's procedure. But that's not what happens these days. There's just a testing of the null hypothesis without specifying a particular number for the alternative hypothesis. The alternative hypothesis is an interval, like not 0 or positive or something like that. And then under this procedure, if you reject the null hypothesis that the coefficient is 0 in favor of the alternative hypothesis that it's not 0, that gives you license to proceed as if it is 0.173, whatever you estimated it to be. So it's not frequentist in the same sense that it's conflating what should be a constant with what should be a random variable, if this was actually done with like repeated sampling. And not only is it not frequentist, it's not something that was advocated by Fisher or Neyman or anybody else in that era. It was something that was invented by journal editors who were left in a quandary as to what papers, frequentist papers obviously back in the day, should be published. But as was known at the time, like 1950 or so forward, there's big problems with this. One, open invitation for p-hacking, in the sense that if, in order to get your paper published in a journal, you have to have the p-value below 0.05 or whatever. It incentivizes you to do whatever you need to do to get the p-values below 0.05 and then stop in order to get your stuff published in a journal, or at least meet a necessary condition for getting your stuff. So the journals just invited p-hacking. And we have like 60, 70 years of experience. That did not go well. Led to implosion of social psychology. But yeah, it's been critically assessed, particularly in recent years. But they're just saying the same thing that people were saying at the time, because it should have been obvious to anyone who looked at it. Also, what should be obvious, the distribution of published point estimates is going to be a distorted version of the distribution of all estimates, published and unpublished. So if you filter, like you have to have the p-value below 0.05 in order to get your stuff published, then what gets published is the most extreme estimates. And so you get bias, but also like huge variance in what is published as compared to the distribution of estimates from all studies, both published and unpublished. But anyway, even though the American Statistical Association has said like no one should be using this procedure anymore, people still do. And so supervised learning has contrasted themselves with this extremely popular but deeply flawed procedure with their own alternative procedure heuristic, which is proceed as if the true parameter is the estimated parameter. But that estimated parameter may well be exactly 0 if you're using a penalty function that is not differentiable at 0, which the lasso or the L1 penalty function is not differentiable at 0 because, as Sarah Van Erp and co-authors pointed out, it's equivalent to using this prior, which involves the absolute value rather than the square of the coefficient, and the absolute value function is not differentiable at 0. So that's why you get this entirely plausible scenario that some of the coefficients are literally 0 at the optimum of the penalized log likelihood function being used there. So the supervised learning procedure is proceed as if the true parameter is the estimated parameter, which may or may not be 0, given the optimal lambda. And the optimal lambda has to be determined, bootstrapping, k-fold, cross-validation, something like that. But if it turns out that some of the coefficients are exactly 0, then you're multiplying 0 by like a column of numbers, and you could just skip that part. So we have a supervised learning procedure to decide whether or not the case predictor should or should not be included in the model that seems to be unaffected by the criticisms that would apply to the somewhat analogous frequentist procedure. But both of those stand in contrast with the Bayesian. I wouldn't really call it a heuristic, it's just the way, which is to proceed with all your draws from the posterior distribution of beta, given the observed data. And none of those posterior draws will be exactly 0, but all of them may be close to 0, in which case you can do a plot to evaluate that. But the thing about these things here is that no one actually really cares if something is exactly 0. What they care about is the parameter or whatever close enough to 0 to where it's negligible, like I could get away with ignoring it. Because both frequentist procedures, if you eliminate the irrelevant predictors, that makes the rest of the predictors better, like more reliable in their estimates, if you get rid of all the junk predictors. Similarly with the supervised learning stuff, if you take the things that are like pretty close to 0 but have high variability and make them exactly 0 with no variability, you tend to get better predictions in the testing data by taking the stuff that's negligible and calling it exactly 0. In contrast with the Bayesian thing, nothing is really hurt by keeping the not very relevant predictors in, because we just get posterior draws of everything, and if they happen to be like pretty small, then they're not going to affect your predictions very much. But the uncertainty in them is real, and so we want to keep preserving that. So let's see how it would look in a case, not the case that we did before, but a logit model. Let's say we fix the intercept to be 0, and we just have one predictor. So I just have a one-dimensional plot here, so we can visualize what's going on. So what we have with the red curve here, so this is on the log scale. What we have with the red curve here is the likelihood, but the vertical axis is log scale, so you can think of this as log likelihood. And so if we were frequentist, God forbid, and we wanted to estimate beta, we would choose the value of beta to maximize the log likelihood function, which is going to be something maybe a little bit less than 2. And then if we were like modern, we would test the null hypothesis that beta is 0, and if we reject it, then we proceed if it's like 1.9, and if we fail to reject it, we would call it 0, and p-hacking and all that. But anyway, to forget about the inference, just the estimate of beta would be whatever maximizes this red function, a little bit less than 2. Everybody can see that? There, okay. So what the lasso does is it includes a penalty function, L1 regularization, the absolute value business summed up. And that in log units has this triangle shape to it. And so if the coefficient is exactly 0, that's the best with regard to the penalty function. So it's penalized to the extent it's different from 0. So if it's exactly 0, that's the best. If it's more negative, more positive, or whatever, it gets penalized according to the black. So that's the penalty function, and then the lasso procedure adds the penalty function to the log likelihood. And so that gives you the blue, which is the numerator of Bayes' rule in log units. And sometimes, actually oftentimes, the supremum of the combined penalty and log likelihood function is at 0, where this is not differential. And so if we maximize with respect to the blue line there, we would get a coefficient estimate of beta that's exactly 0, in which case we could drop this predictor from the model because it gets multiplied by 0 anyway. So frequentist perspective, we're over here. Supervised learning perspective says, well, this maximum likelihood tends to overfit and predicts future data worse. Because maximum likelihood, it really should be named maximum overfitting. It produces the values of the parameters such that the most likely data set to observe is the data set you did observe. And consequently, it's going to fit a little bit worse for any data set other than the data set that you observed, such as future data. So maximum likelihood tends to overfit and predict badly, or at least worse in future data, than pretty much any supervised learning field does. But what supervised learning does, it incorporates the penalty function, and it shifts the supremum from like 1.9 in this case to 0 in that. And doing so, not in every case, but in general, tends to yield better predictions of future data. If you make the like not too big stuff be exactly. But from a Bayesian perspective, to proceed as if it's exactly 1.9 or proceed as if it's 0 are equally ridiculous. Because we have a whole posterior distribution in blue here. Not a very precise one, because this example only had like 8 data points or something like that. But we have a posterior distribution. Yeah, the most likely value under the posterior distribution is 0. But 0 has no width on the real line. And so it's most likely positive. The median is positive. The mean is positive. It could be negative. There's a good chance it's negative. But a bigger chance that it's positive. And so the Bayesian procedure produces the whole blue here, or draws from the distribution, whose PDF is this blue line here. And so we're reflecting our uncertainty about those and about the true parameter from the variability in the draws that we get from the posterior distribution. And this is extremely important because in a lot of situations, you don't, from a Bayesian perspective, you don't have an overfitting problem to the data that you conditioned on if you consider how well the model fits the data averaged over the whole blue. The so-called overfitting problem emerges when you take a point estimate, either the red or less so 0 for the optimum there, because you're evaluating the fit only at the most optimistic point in the whole parameter space. 1.9 in the case of maximum likelihood. You took literally the most extreme point with respect to the log likelihood and evaluated the fit there only, ignoring all uncertainty in the parameter. If you get like draws all throughout the posterior distribution with the appropriate weight, evaluate the fit in marginalizing over the parameter uncertainty, and then take the expectation of it for future data, you'll often find that your fit to the data that you conditioned on is essentially the same as the fit to future data, if that future data came from the same data generating process as the past data. And so it's slightly true, you can overfit with Bayesian stuff, but that the fact that it's slightly true obscures the bigger point, which is that the overfitting phenomenon is primarily induced by the use of point estimates and ignoring all uncertainty, evaluating the fit only at the point estimate, as opposed to evaluating it at every posterior draw and averaging the good and the not so good and the pretty good together. And then you get this value of fit for the data that you conditioned on, which is worse than if you just did the maximum likelihood thing and stopped. But because it's worse than just doing the maximum likelihood thing and stop, it tends to be better than the maximum likelihood estimate for predicting future data. And it tends to not have overfitting problem at all. And if you do, it's usually because you use some ridiculous priors, too weak, or otherwise that gave you a prior predictive distribution, which was crazy. But even if you do, you'll know because we can do the posterior predictive checks and we can get the estimate log predicted density. And so you estimate two models and one of them like overfits a lot more than the other one. It will have a worse expected log predicted density for future data than the model that is better calibrated. And so, big picture, because we're out of time, overfitting is mostly due to point estimation, which is a choice, and you don't have to make that choice, you should not. When you do have overfitting, even when you use MCMC, it's mostly because your priors were dumb. But even if you do, you should be able to tell that your model is not fitting so great with posterior predictive checks and comparisons of estimated ELP. Okay, so all we have time for today. Tuesday, as usual, recitation and office hours, and keep posting questions.